This is an introduction about a thermal coupling with MpCCI, Abaqus, and Fluent simulation codes. The thermal cosimulation is an exhaust manifold case. We have a solid part and fluid area. And this example will deal with a steady state cosimulation. We have here the characteristic of the solid model with the material properties that will be implemented in the Abaqus model. We have roughly 15,000 elements on the Abaqus side. On the fluid model side, we have modeled the fluid with air and with following characteristic of the velocity inlet in red, which are modeled with 6 meters per second and inlet temperature of 600 Kelvin. So in our case, we need to compute a first standalone CFD calculation where we will load the Fluent model and compute an initial steady state flow simulation for 200 iterations. So let's have a look on this calculation. We have here Fluent version 2021 R1 version, and we will load the case file of the model provided by MpCCI. After the case has been read, you can initialize the flow by using standard default settings. After the flow has been initialized, you can enter the run calculation task of Fluent and provide the 200 iteration and click on calculate. So now we will reach the end of the 200 iteration number. The solution is completed and we can, with write data, save the solution data of Fluent, and we can exit the Fluent simulation code. Now we can use the MpCCI graphical interface that you can call by using the command line MpCCI GUI, and you can, in the first step called model step, select the simulation code you want to use. Abaqus, in our case, specified the release you want to use for the calculation. We will take the latest one, which installed on our current machine is 2021. And then the next step is to select, for example, the input file. We will browse into the tutorial folder of MpCCI, where we have separated each simulation files by the code. We look for Abaqus and we have the ENP file, which we can select. The model file will be parsed by MpCCI and information of the boundary condition will be extracted. We do the same thing for the CFD part. We select Fluent. We can specify the release of Fluent to use and select the case file of Fluent. So we have loaded our simulation file, and in the next step of the setup, we will have to define in the algorithm step here in the documentation the type of coupling algorithm we want to use. In that example, we want to use a parallel scheme, and the fluid mechanics code will initialize the Cosimulation. And in our case, we will have a maximum number of 20 iteration of data exchange, which has been to set up. How it looks like, we go to the next algorithm step, and we can choose the algorithm type to use. So in our case, we're interested in a parallel type, and we activate the initialization part. And as we have an initial CFD solution, we would like that this simulation code sends the initial film properties to Abaqus. In our co-simulation, we would like to have a maximum number of 20 data exchange. And in our case, we can see that both input models will do a steady state calculation. We do not require the subcycling option on Abaqus side, and we would like to define the coupling step size. So we have defined in Abaqus model, we have a total number of 20 increment set in the input deck, and we would like to exchange at every increment of time steps 1, have an exchange of the data on Abaqus side. On the Fluent side, we would like to do some subcycling calculation for the CFD part, and in order to reach that calculation of subcycling, we can provide a number of 10 iteration or solver steps, which defines the step size for the co-simulation. So we have now defined the algorithm step, and if we go back to the documentation, the next step will be the region step. In the region step, the goal, the target is to select in that page, select the different boundary conditions which have to interact each other. We have different icons to represent different dimensions of the boundary conditions. On Abaqus side, we have some points, surface, and volume information, as well as on Fluent side. On Fluent, we just have surface definition and volume definition. In our case, we are interested in the surface co-simulation interaction, and we know in advance, in our case, that the inner surface part of Abaqus will be in interaction with the fluid domain. So we double click to select the regions, the part of interest, and on Fluent side, this section which corresponds to the inner surface of Abaqus is named wall. After defined the regions of interaction, where the interaction takes place in the space, we move to the quantity definition, and we have some predefined setting coupling type. We can use a setting, so we want to do a surface, and the default settings will be activated by MpCCI. We exchange some film properties based on film temperature and wall heat transfer coefficient computed by the CFD code Fluent, and Abaqus will compute the resulting wall temperature back. So if you click on one quantity, you see the direction of the data transfer from Fluent to Abaqus, and some additional operations are available. If you have to deal with some partial overlapping of the mesh, you can define how this partial overlapping area should be handled by MpCCI if the data should be treated with a default value you want to define, or you can define activate extrapolation if you like. If you want also to accelerate some the Cosimulation process, you can also use some operation like relaxation. If you activate, you have some different option to use. In our case, this is not really needed. So if you check for the wall temperature, it will be computed by Abaqus and sent to Fluent in our case. After having defined the first quantity set, we need to go to the quantity set assignment section, and for this first region we have to select the quantity we want to apply it on it. And we can see with a double direction arrow symbol that we have a bidirectional data exchange on that region. So now we have complete the setup of the cosimulation definition and algorithm, and basically we can go directly to the go step, the final step. In this last step, we mainly define the runtime of the simulation codes. We can define the number of processes to be used for the computation, activate some thread, or run Abaqus with a distributed memory model based on MPI. Same options are available on the Fluent side. You can activate the parallel processing of data for Fluent and specify the number of processors to be used. In our case, we have done a first initial computation of data on Fluent side, and we would like to load this simulation results and click then on the data file section for browse, which opens the file selection directly inside the Fluent model folder, and we can see the previously saved data solution of Fluent. We need to select it, and after having selected the data input file, we have basically complete our setup. If you have a look on the documentation on the Go section part on Abaqus side, we do not need to do something. On Fluent side, we have selected the data file, and we need to deselect, for example, the auto set MDM. So this is for the moving dynamic mesh option. In our case of the manifold example, we do not have any moving section, so we can deselect that option. For the other options, MpCCI will create at runtime a journal file which will provide the command to Fluent to read the case and data files that we have selected. It will load automatically the library for the cosimulation inside Fluent and hook the necessary boundary condition in order to exchange the data information on the mesh for our thermal cosimulation. Before starting the cosimulation, we need to save the model. We can say Exos manifold and save, and we are ready to start our cosimulation. By clicking on start, we will have a check is running in the background, and in the background we will have different processes which are started by MpCCI. And if we minimize the MpCCI GUI, you can see here the Fluent graphical interface which is started. Some output is done. The initial journal file created by MpCCI has been read by Fluent, and we have in the other background running here, we can see the output of the Abaqus solver, and you can see that in our example, Abaqus has been initialized and is connected with MpCCI and is waiting for Fluent. In the Fluent model, if we just have a quick look on the boundary condition at the wall, we see we just have one boundary condition. If we just edit it before we begin the calculation, we can see that on the thermal part, the thermal condition is defined by temperature condition, and we can see that the definition is done over a user-defined function, and this is in that way that the temperature profile will be imported from Abaqus in Fluent. So the setup has been completed automatically by MpCCI in that case. Now on Fluent, we have loaded the initial data file, and now we just need to provide the number of iteration we want to use, and just click on calculate. In the background, the MPCCI monitor tools has been started. You can see in that window the different mesh definition that has been defined for the Cosimulation. You can see the type of the mesh for the Abaqus model. If we activate Fluent, you can see there that both models has different mesh discretization. In addition to the mesh visualization, you can go to the results section, and by activating the results quantity, you can see the temperature contours. If we deselect, for example, the mesh model for a better representation, we can see the current film temperature, which is computed by Fluent, and how it is mapped on Abaqus side. And this is a way to follow the process of the Cosimulation. In the background, Fluent has completed the 200 iteration. The calculation is complete. If we switch back to the Fluent to the Abaqus output window, we can observe that the Abaqus solver has finished his calculation. A total amount of 20 increments was set up, and the Abaqus job successfully reached the end of the calculation. And if we want to have a quick comparison of the data exchange, we can go to the Fluent section and plot the temperature on the wall, which should match. We move the compute. It should match then the results sent by Abaqus. Let's have a look on the Abaqus results. So in that case, we select or just open one viewport for Abaqus, and we will activate the wall temperature. We will reconfigure the range setting, activate to the last data sent at the final iteration Cosimulation step number 20. And if we compare the contours of the data, what Abaqus has sent to MpCCI and what Fluent has imported from MpCCI, we can see that the temperature range match and the Cosimulation has been successfully realized. So you can visualize inside Fluent the Abaqus wall temperature, which is perfectly matching the presentation inside the MpCCI monitor. So this is an example of the Cosimulation with Abaqus Fluent for a thermal simulation of an exhaust manifold. After you have finished your post-processing of your data, you can exit the Fluent calculation and you can see in the MpCCI GUI interface the simulation has been finished and everything is indicated as done.